अस्सलाम वालेकुम स्टूडेंट्स। ये आपका सेकंड लेक्चर है। फर्स्ट लेक्चर में हमने डिस्कस किया था इवन और ऑड फंक्शंस को। A function f of x is said to be an even function if we put f of minus x and the answer is equal to f of x, and the function f of x will be considered as an odd function if we put f of minus x and the answer will be equal to minus f of x. So the other function, which is neither even nor odd, is called neither even nor odd function. So we also discussed about some examples in the last lecture of even and odd and neither even nor odd functions. So we also defined some rules, general rules, in which if we find the product of two even function, the result is always be equal to an even function, and if we have a product of two odd function, again we will get an even function. And if we have an even function and odd function, and will have to take the product of these two functions, the result will be an odd function. So now let's discuss about the integration of even and odd functions. So how we will define some general rules about the integration of even function and integration of odd function. So here we have an odd function over a symmetric wave. So we assume that p, an integral which is integrated from minus p to plus p, and the function is f of x dx, which is equal to 0. When it will be equal to 0? Why? Because we have seen in the last slide that the odd function has symmetry around the origin, and the even function has symmetry along y-axis. So if we consider a symmetry around the origin, then we'll see here that from in this minus a region and plus a region, which are opposite to each other, and these regions will be cancelled the effect of each other. So the area beneath the curve minus p to 0 is the same as the area under the curve from 0 to p, but these two areas has opposite sign, so they will cancel the effect of each other, and the integral from minus p to plus p f of x ds will be equal to 0. So here we will see the integration of an even function over symmetric domains. So again we assume that p is greater than 0, be any fixed number. So if we have a function f of x which is an even function, then the integration from minus p to plus p of a function f of x dx will be equal to twice of the function which is integrated from 0 to p f of x dx. So here you can see from this graph, this symmetry is around y-axis. So these both areas from minus p to plus p 0 and 0 to plus p, that areas are same. So their sum will be added, and we will get a function, an integration twice of we'll get a double function. So we can just find the area under the curve from, if we have if we have to integrate a function from minus p to plus p, then you can only write here the twice of the function from 0 to p f of x dx. Now we here summarize of the two functions, one is even and one odd. So for the integration of an odd function from a region minus p to plus p is equal to considered as a 0, and the integration of a region from minus p to plus p is equal to twice of the integration from a region 0 to p f of x dx. So now we have to discuss another important term called orthogonality. So here we will consider the region of integration from minus pi to plus pi, and we will consider sine and cosine functions that can be used in this way because they satisfy the following orthogonality conditions. Which conditions they satisfy? Here we will divide three regions, three different integration. One is the product of sine and cosine, the other is product of two functions, both are sine, and the third one is the integration of two functions, both are cos. So first we will consider two functions, one is sine and other is cosine, and if we have to find the integration of these two functions from minus pi to pi region plus pi region, their integration will be equal to 0. Again I repeat, if we have to find an integration from a region minus p to plus p, and the functions are the product of two functions, and one is sine and other is cosine function, then this integration will be equal to 0 for values m and n, for all values of m and n. So we can say that sine nx cos mx dx from minus pi to plus pi is equal to 0 for all values of m and n. So let's see another integration, or the product of two cosine functions from a region minus pi to plus pi. So here you can see that cos mx and cos nx dx is equal to 0 when m is not equal to n. So we will have three possibilities in this integration. One is when m is equal to n, and which is equal to 0, mean m and n both are equal to 0. And the other possibility is when m and n both are equal but greater than 0. The third possibility is when m is not equal to 0. Sorry, m is not equal to n. So in the first, if we consider the first possibility where the m is not equal to n, this integration will be equal to 0. In the second possibility, when m is equal to n is equal to 0, this integration will be equal to 2 pi. So here we also consider the case that we have discussed in even and odd function. If the product of two even function, the answer will be equal to an even function. And if we integrate an even function from a region, we'll see the slide, from region minus p to plus p, this integration will be answered in the 2 of the region from 0 to p f of x dx. So this is the even function, and the answer will be equal to 0 for the values m is not equal to n, and this integration result will be equal to 2 pi when m and n values will be equal to 0, and this region will be equal to pi when m and n both are equal each other and greater than 0. So let's see the product of two sine functions, and region is again from minus pi to plus pi. So here we will see two conditions. One is in which m is not equal to n, the other is m is equal to n and they are greater than 0. So in first condition, where m is not equal to n, the integration result in this region is equal to 0, and in the region where m is equal to in the integration where m is equal to n and which is greater than 0, the integration result is equal to pi. So here we will note an important result, that the integral only needs to extend from minus pi to plus pi or any other period of 2 pi, as the function simply repeats outside this range. So we already have discussed about the periods in which a periodic function repeats itself. So this is very important result, and these results will be used further to solve the Fourier series questions. So here we will find some coefficients which will be used in the Fourier series. The orthogonality condition allows us to pick values for all the coefficients. Multiplying whole Fourier series by 1 cos nx or sin nx and integrating over a region to terms which are 0 apart from 1, which correspond to the coefficient, which are the coefficients a0, an and bn respectively. So you can write the coefficients a0, an and bn. We can define these coefficients. a0 is equal to 1 over pi from the region minus pi to plus pi f of x dx. The other coefficient an is equal to 1 over pi minus pi to plus pi f of x cos nx dx. So the third region is bn, 1 over pi, region is from minus pi to pi f of x sin nx dx. यहाँ पे जो हमने कोफिशिएंट्स देखे हैं, ये कहाँ पे यूज़ होंगे और इनके क्या एडवांटेजेस हैं, ये कोफिशिएंट हम क्यों ले रहे हैं, ये सारी बातें हम डिस्कस करेंगे जब हम फोरियर सीरीज़ को के क्वेश्चंस को या फोरियर सीरीज़ को जब डिफाइन करेंगे. सो हमारा ये लेक्चर यहाँ तक ख़त्म होता है. नेक्स्ट लेक्चर में हम फोरियर सीरीज़ को डिटेल से सॉल्व भी करेंगे, उसके रिलेटेड क्वेश्चंस को सॉल्व करेंगे और हम देखेंगे कि जो a0, an और bn कोफिशिएंट्स हैं उनके क्या फ़ायदे हैं और उनको कैसे हम फाइंड आउट कर सकते हैं. और जो हमने पीछे ऑर्थोगोनैलिटी कंडीशंस पढ़ी है, इवन एंड ऑड फंक्शंस को पढ़ा है, ट्रिग्नोमेट्रिक फंक्शंस को पढ़ा है, ये सारे जो हमने टर्म्स पढ़ी है, वेवलेंथ को पढ़ा है, सारे की सारी टर्म्स आगे फोरियर सीरीज़ के क्वेश्चंस में कैसे हमारे लिए हेल्पफुल हो सकती हैं. तो काइंडली इनको आप जो है वो इनको आप लर्न करें, इन टर्म्स को सीखें. क्योंकि ये काफ़ी ज़्यादा आपको आसानी होगी फोरियर सीरीज़ के क्वेश्चंस वगैरह सॉल्व करने में। तो यहाँ तक ये लेक्चर एंड होता है। थैंक यू वेरी मच।